Hey everyone. So today is the first lesson of trig equations. We're going to start looking at solving equations. And what I'm hoping is that most of what we do today, although it's new, the goal is I always want you to look for what's familiar. The first half of this lesson, we're going to talk about solving trig equations graphically. Well, you've already done other equations graphically, and solving trig equations graphically is no different. So I want you, especially just to kind of help with the stress level. I know that trig can be very, very stressful. I want you to always keep in the back of your mind, this is familiar to what I've already done. The difference is now I have to do it inside trig, and that's where it gets just a little bit messy. So here we go, solving trig equations graphically. Now, first question here, it says that the graphs of y equals 5 cos theta plus 5 and y equals 3 cos theta plus 4 are shown. Label each graph with the correct equation. Now mine are green and blue, yours are not, but take a look at them and try and decide, how do I know which one's which? Well, you know both those graphs midline and their amplitude. You know that the 5 cos theta plus 5, that has a midline of 5 and an amplitude of 5, meaning I have to go up 5 from 5 and down 5 from 5, from y equals 5. So that's going to have to be the green graph. Same thing with y equals 3 cos theta plus 4. I get a midline of 4, you can see that right here. And from there, I'm going up 3 and down 3. So you should label what is my green graph as y equals 5 cos theta plus 5, and label my blue graph as y equals 3 cos theta plus 4. Okay? Now, easy. See, we're off to a great start. The next guy says, explain how the graphs above can be used to determine the solution to 5 cos theta plus 5 equals 3 cos theta plus 4. Well, you guys have been doing this for the last couple of years. When we're solving, left side is one equation, right side is the other equation. If we were going to do that in a graphing calculator, what would we look for? We would look for the x value at the point of intersection. So that's all we would do here. The solutions would be the theta values. Theta is just x at the moment. The theta values of the points of intersection for the two equations. So what are they? If I'm going from negative 2 pi to 2 pi, so that means I'm going from here, if you see my mouse, all the way to here. That's the window that I'm looking for solutions. So right now, that's the window where I'm looking for those points of intersections. Well, I can see one here, I can see one here, I can see one here, and I can see one here. So now, what are those guys? If I look at the scale, I've got 1, 2, 3 tick marks to pi. That one's negative pi, but it's 3 tick marks to pi. So that means this first intersection point is at 1, 2, 3, 4. So negative 4 pi over 3. This guy would be 1, 2, 2 pi over 3. Because it's 3 tick marks to pi, every tick is pi over 3. And then this guy is 2 pi over 3, and this guy is 4 pi over 3. So, rewrite those, oh, sorry. Get my mouse back. Rewrite those guys here. Negative 4 pi over 3, negative 2 pi over 3, 2 pi over 3, and 4 pi over 3. Now, are there any other values for theta that satisfy the equation 5 cos theta plus 5 equals 3 cos theta plus 4? Explain. Well, actually, you saw one. You can see one right here. Hey, that's another intersection point. One over here, that's another intersection point. The fact that I've given you a few periods here is kind of our hint to say, hey, don't forget, these intersection points are going to happen at regular intervals for all of infinity. So there's actually an infinite amount of answers to this question. So I said yes, because both graphs are periodic, they will continue to intersect at intervals of 2 pi from the first two solutions. So remember, we talked a couple lessons ago about general solutions when we were talking about the asymptotes, actually with tan. And then when we first, even before that, we started talking about general forms of coterminal angles. So we always want to state our first positive. So that'd be this guy here. That guy there is 2 pi. So 2 pi plus sorry, 2 pi over 3, that was my mistake, sorry, 2 pi over 3, 2 pi over 3 plus 2 pi intervals after that, and 4 pi over 3 is the other guy. We have to say this in 2 statements. The reason we have to say this in 2 statements is because if it was 1 statement, I'd have to say, okay, well, how do I go from there to there? That would be like, I'm going to add 2 pi over 3. But then when I add another 2 pi over 3, I don't get a solution. So that's why we know we have to say this in two different statements. So the first one would be 2 pi over 3 plus 2 pi n, and the second one would be 4 pi over 3 plus 2 pi n, where n is a member of the integers. So that's written in your notes here. And then it says, use the general solution to find 2 more solutions outside the domain of number 3. So all you have to do, you can take the 2 pi over 3 and the 4 pi over 3 and just add 2 pi to them. Remember, anytime you add 2 pi, that's a coterminal angle. So if you think about the unit circle, you're right back where you started. It's just you've rotated more. Likewise, I could also have taken negative 2 pi over 3, this guy here, or negative 4 pi over 3, and I could have gone backward, so I could have subtracted another 2 pi, and that would have given me a coterminal angle as well. But for this question, I just added 2 pi. So I said 2 pi over 3 plus 2 pi is 8 pi over 3, and I can do that in my head. Don't stress. 2 pi as a fraction over 3 would be 6 pi over 3. 6 divided by 3 is 2. So it's just like saying, okay, well, that's 2 pi over 3 plus 6 pi over 3 is 8 pi over 3. Then likewise, 4 pi over 3 plus that 6 pi over 3, which is my 2 pi, would give me 10 pi over 3. Okay? So now what we want to do is we just want to play around with what we call restrictive domains. So in this first example, we kept you at negative 2 pi to 2 pi, and you had 4 different solutions. Then we said, hey, there's an infinite, so let's write the general solution. Now we're just going to play with different types of windows, different pictures of the graph, and how you have to decide what your solutions are within that new window. So there's 2 tables of 4 here. Just for purposes of not trying to squish everything on the slide, I'm just going to do the first 4 with you, and then we'll go and do the next 4 together. So the first 4, we've got 0 to 2 pi. Now, 0 to 2 pi means we're just looking at the positive answers. So I would be looking at just this guy here and this guy here. So my answer would be 2 pi over 3 and 4 pi over 3. For the second guy, I'm allowed to go to negative 4 pi over 3 all the way to 4 pi over 3. And you want to pay attention to these guys here, okay? This says I can equal, which is good. That means I can be the negative 4 pi over 3 and I can be the 4 pi over 3. So for this guy, there will be 4 different answers, the plus or minus 4 pi over 3 and the plus or minus 2 pi over 3. You need to be careful of that though, because sometimes we will just say less than and not say less than or equal to. And then it can't be that endpoint if I don't have that equal to sign. So that does come up in testing. So you just want to make sure you're watching that very, very carefully. Okay, the next guy is from negative 4 pi all the way to 4 pi. Now you don't see the picture of that here. I only go to just a little over 2 pi, almost 3 pi there. But you know how to get the coterminal angles. So that's all you have to do. You take the angles that you have, add or subtract 2 pi, and make sure you're still within that window, okay? So for this guy, we actually talked about that on the previous slide. We ended up getting the 8 pi over 3 and the 10 pi over 3. Because I'm allowed to go all the way to negative 4 pi and all the way to positive 4 pi, I can be plus or minus 2 pi over 3, plus or minus 4 pi over 3, plus or minus 8 pi over 3, and plus or minus 10 pi over 3. Then this fourth one, I go from 0 to 2 pi over 3. So I'm going from 0 only to here. So again, sometimes it's helpful, like just even box what your window is, right? Where I'm boxing the y doesn't matter. I'm just trying to show you I can go from, oh, that was my mistake. I'm going to clear that. If I'm going to box it, I might as well box it right for you. Hey, I can go from 0. I'll just leave. I won't actually box it. 0 to 2 pi over 3. That's where I'm allowed to be right now. Okay, so there is one solution there. It's at 2 pi over 3. So then I have to ask myself, can I be 2 pi over 3? Because that's an equal sign there, I can be 2 pi over 3. So that's good to go. I have one answer here at, oh, sorry. at 2 pi over 3. Okay, so now you should pause me now. You try the last four, and I'm going to go through those in 1 second. So from negative pi to pi, that means I'm going from here to here. So that would just be the plus or minus 2 pi over 3. I don't have any of the 4 pi over 3s there because that's with outside of the domain. Negative 4 pi over 3 to 4 pi over 3. Now, this looks like one I just asked you, but it's not, and this is what I need you to see. I didn't give you the equal signs there. So I can't be negative 4 pi over 3, and I can't be 4 pi over 3, and those happen to be what my next solutions would be. So for this guy, it is still 2 pi over 3, plus or minus. Negative 2 pi to 0, that would just be the negative versions, negative 4 pi over 3 and negative 2 pi over 3. And then 0 to 2 pi over 3, that's like the fourth one I gave you on the first table, except I can't be 2 pi over 3 this time, and 2 pi over 3 was actually my only solution in that set. So there is no solution. You have to say no solutions. Don't say 0 because 0 is a number. Say no solutions. Okay? Awesome. Okay, so now, new graph. The graph of y equals 2 cos theta plus 1 is shown. Use the graph to solve each of the following within the domain of negative 2 pi to 2 pi. So 2 cos theta plus 1 equals 0. Again, just think of this like a system of equations. I don't want you to graph this right now. You don't need to. You're just going to look at the picture. But you could graph it in your graphing calculator if you needed to. You'd put 2 cos theta plus 1 in y1 and 2 cos theta, or 0, sorry, in y2. Well, you've already got 2 cos theta plus 1 graphed. It's right here. So we just have to add y equals 0 to that. Y equals 0 is the x-axis. So here I go. I'll add in a line on the x-axis. And now I can see where my solutions are. My solutions are here, which happens to be, now take a look at my tick marks, 1, 2, 3, 4, 5, 6 steps to pi. That means every tick is pi over 6. So that's 6 pi over 6, 7, 8 pi over 6. So that would be negative 4 pi over 3 when I reduce. And this guy is 1, 2, 3, 4 pi over 6, which would be negative 2 pi over 3. Same on the other side. Be careful, don't always assume that it's positive and negative. I know in the first example it was, and in this example it was, but that's because the graph we've drawn was symmetrical over the y-axis. So if it's not symmetrical over the y-axis, you're not always going to get those beautiful plus minus all the time. So you got to make sure you are counting and that you're seeing where the solutions actually are. 1, 2, 3, 4, and then 5, 6, 7, 8. They are in the same spot for the positive version as well. So for this guy, it'd be theta equals plus or minus 4 pi over 3 and plus or minus 2 pi over 3. Okay, what if we did 2 cos theta plus 1? Well, same thing, except now instead of y equals 0, I'm going to draw in y equals 1, and I'm going to look for those intersection points instead. This is the halfway point, so I'm looking at actually negative half pi and negative 3 pi over 2, and then half pi and 3 pi over 2. Okay, so what if it's 2? Well, same thing. Instead of drawing a line at y equals 1, we're going to draw a line at y equals 2. So I draw a line at y equals 2, and I look, pardon me, I have 1, 2, so that would be negative 2 pi over 6 or negative pi over 3. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 pi over 6 would reduce to 5 pi over 3. So plus or minus negative 5 pi, plus or minus 5 pi over 3, and plus or minus pi over 3. Now, don't let the wording of the next question throw your game off. Think about what we've been doing for these 3 questions. The next question says, find the value of y so that the equation y equals 2 cos theta plus 1 has the general solution of theta equals 2n pi or 2 pi n. Don't let that confuse you. It could be written either way. Where n is a member of the integers. Now, this is a general solution. But we've talked about the fact that to write a general solution, you're always writing the first positive and then your period of repetition. What I want you to notice here is there is no period of repetition. It goes right to that 2n pi. That means that the first positive is 0. Nobody's going to say 0 plus 2n pi. They're just going to say 2n pi. So this becomes a fancy way of saying 0 equals 2 cos theta plus 1. Well, we've actually already done that. We've already found the solution to that. So the positive answer is our general solution is 0. So there's where I'll have 0, which means I'm looking at y equals 3. So had this equation said 3 equals 2 cos theta plus 1, that would give me the general solution of 2n pi. Okay? All right. The graph of y equals 2 cos theta plus 1 can be shown, or can be used to solve the equation 5 cos theta plus 5 equals 3 cos theta plus 4. Explain and show how. Now, we're just trying to pull a couple things together here. Notice that the 5 cos theta plus 5 and the 3 cos theta plus 4, that was actually the two graphs we originally gave you. Then we switched to this new graph that was y equals 2 cos theta plus 1. We're saying, how could I use y equals 2 cos theta plus 1 to solve for 5 cos theta plus 5 equals 3 cos theta plus 4? Well, let's just do some math with this guy. So if I went 5 cos theta plus 5 equals 3 cos theta plus 4, and I started trying to simplify it, let's bring everything over to one side. So in order to simplify this, what I might do is I might subtract 4 from both sides, just trying to bring everything over. I might subtract 3 cos theta from both sides. And what that's going to give me is 0 equals 2 cos theta plus 1. Well, 2 cos theta plus 1 is actually that equation. So this equation, if I set it equal to 0, that's helping us figure out what the answer to 5 cos theta plus 5 equals 3 cos theta plus 4 is. Okay, so I said here, if we simplify the original question by bringing everything over to one side, we end up with 0 equals 2 cos theta plus 1. This is the graph we were just dealing with. So we look at the x-intercepts of the graph of y equals 2 cos theta plus 1. Now that was a question we had just done previously, so I'm just going to bring that back up. Those are the x-intercepts, and my solutions was plus or minus 4 pi over 3 and plus or minus 2 pi over 3. Okay, so that was the graphing portion. Now we're going to turn our attention to just some solving algebraically. Now the solving algebraically today, we're going to keep fairly innocuous. It's not going to be like super hard. Tomorrow we're going to get into more quadratic looking trigonometric equations. But for today, we just want to get you going again. This is going to look very similar to the stuff we did right after we talked about our unit circle, okay? Things are going to feel very much the same. So if you have a good understanding of your unit circle, the algebraic portion of today is not going to be hard. So we've got two forms of writing trigonometric equations, either the function form where we have y equals, or the equation form where we have 0 equals. Sorry, that should say 0 there. That's a typo that I'll fix before I post this. As with all equations, we can solve algebraically or graphically. We just did the graphing, so now we're going to go and do the algebra. So solve for cos theta plus 2 equals x in the domain 0 is less than or equal to theta is less than 2 pi. Now, how am I going to get theta by itself? Okay. In everything we do, we're trying to get that unknown all by itself. Well, think logically. If cos of x, if cos of theta was an x, how would you get it by itself? You'd subtract 2, you'd divide by 4. So all of those things that you already know how to do, those are the things you should be trying here. So we subtract 2, we divide by 4, and that gets us to cos of theta equals -1/2. Well, now I'm on my unit circle. Cos of theta equals -1/2. Where does cos of theta equal -1/2? Well, let's just think about reference angles first. Let's just think about cos of theta equals 1/2. Then we only have to think about the first quadrant for a minute. If cos of theta equals 1/2, my reference angle is pi over 3. Then, because cos of theta is negative, we know that we have to be in quadrant 2 and in quadrant 3. Just think about the cast rule. Put that up so you can reference it as we go, okay? So I need to think about a reference angle of pi over 3 in quadrant 2 and in quadrant 3. So that's going to give me an answer of 2 pi over 3. That would be the quadrant 2 guy, which if you can't do that in your head, that would be pi minus the reference angle, right? So pi minus pi over 3 is 2 pi over 3. And then 4 pi over 3 would be my pi plus my pi over 3 reference angle. Okay, so 2 pi over 3 and 4 pi over 3 for the first guy. The second guy, now there's a very important conversation to have with this guy. Solve 2 cos theta sine theta equals sine theta in the domain, same domain, 0 to 2 pi. What students want to do right off the bat is they look at that and they say, hey, let's just divide out sine. You can never divide by a trigonometric function. That's a super important point to realize. If you divide by a trigonometric function, you wipe out half your answers, and that's kind of unfortunate. So never divide out a trigonometric function. You'll lose half your answers. Think about it instead from a factoring standpoint. Instead of dividing that out, you want to factor it out, because when you factor it out, it doesn't actually go away. So remember the rules of factoring. In order to factor, everything has to equal 0. So the first thing I'm going to do is take that sine of theta and bring it over to the left. So I have 2 cos theta sine theta minus sine theta equals 0. Now I can factor out the sine theta, and I've got sine theta. What's left when I divide that out through factoring is 2 cos theta minus 1. This is the zero product principle. It's a number times a number equals 0. Think back to all your factoring days of grade 10 and grade 11. So either sine of theta equals 0 or 2 cos theta minus 1 equals 0. One of those has to be 0 in order for this statement to be true. So I just break it up into 2 little trigonometric equations. If sine of theta equals 0, I go on my unit circle. I'm looking for, remember Calgary Stampede, I'm looking for when the y value is 0, that would be at 0, pi, and 2 pi. When cos of theta equals a half, I'm in quadrant 1 and I'm in quadrant 4, and I have a reference angle of pi over 3, so I've got pi over 3 and 5 pi over 3. So now I look at all these answers, and then I go back to my original domain and say, okay, are all these answers viable, and is there any more? There isn't any more because I was only allowed to go from 0 to 2 pi, but also the thing I need you to catch here is 2 pi is not viable because it can't be part of the solution set. It's not actually part of the domain. So my final answer would just be 0, pi over 3, pi, and 5 pi over 3. It's important to write those in solution brackets, and when you write them in solution brackets, it is better to write them smallest to largest. It's better communication. Okay? Next guy then, solve cosecant of theta equals negative 1.5. Now don't let the cosecant bother you. Remember that the cosecant is just the reciprocal or the flipped version of sine. So instead of writing it as cosecant, because I can't really do much with cosecant, write it as sine instead. If cosecant of theta equals negative 1.5, then the sine of theta equals the reciprocal of that, which is negative 1 over 1.5. Now, this is not on the unit circle in the sense that it's going to be a pretty value. So we're going to have to actually arc sine or inverse sine it. So we're going to go the reference angle of theta is the arc sine of 1 over 1.5. And when I do that, theta's reference angle is 0.7297. Okay, remember when you go to arc sine, you're always arc sining the positive version. You never deal with the negative, and then that will always give you the reference angle. Now that I know the reference angle, I think, okay, my sine ratio is negative. Where is sine negative? Sine is negative in quadrants 3 and 4. So I need to apply that reference angle to quadrant 3 and to quadrant 4. In order to apply it to quadrant 3, I'm going to have to go pi plus my reference angle. And in order to apply it to quadrant 4, I'm going to have to go 2 pi minus my reference angle. So one answer is pi plus the reference angle, which ends up being 3.87 when I round it to the nearest hundredth. And the other guy was 2 pi minus my reference angle, which ends up being 5.55. Okay. All right. Solve negative tan theta equals 1 in the domain 0 to 4 pi this time. I can be 0, but I can't be 4 pi. So I need to divide both sides by negative 1. So I get tan by itself. So tan of theta equals negative 1. Now, I can go straight to my unit circle on that. The reference angle is going to be pi over 4 if I have a ratio of 1 for tan. And I know that tan will be negative in quadrant 2 and in quadrant 4. So I'm going to write all that down. I've got a reference angle of pi over 4, tan is negative in 2 and 4. So I have to apply that into 2 and 4, apply that reference angle. The reference angle of pi over 4 here ends up being pi minus pi over 4, which would end up being 3 pi over 4. And this guy would be 2 pi minus pi over 4, sorry, which ends up being 7 pi over 4. So 3 pi over 4 and 7 pi over 4. Now, that's only from 0 to 2 pi. I think one of the better ways to do this, though, is to always just go from 0 to 2 pi. That's what we're comfortable with. We know what our unit circle looks like. We know how to handle our unit circle. Always pretend that you can go from 0 to 2 pi and get those answers first. Then you're going to go back to the domain. You're going to look at it and say, okay, are all of these allowed? And are there coterminal ones that I have to add? Yes, 3 pi over 4 and 7 pi over 4 are both allowed, but because we're allowed to go all the way to 4 pi, I can add 2 pi to both of these guys and get coterminal angles that are still within my domain. So what is 2 pi as a fraction over 4? That would be 8 pi over 4. So 3 plus 8 is 11. So 3 pi over 4 and 11 pi over 4 are coterminal. And then 7 plus 8 is 15. So 15 pi over 4 is also a valid answer. So theta equals 3 pi over 4, 7 pi over 4, 11 pi over 4, and 15 pi over 4. Okay, all right, to determine the general solution to 3 tan theta minus root 3 equals 0. Again, I'm trying to get tan of theta by itself. I want to add root 3 to both sides. I'll divide both sides by 3, and that'll get tan of theta all by itself. And it gives me tan of theta is root 3 over 3. Now, that's on my unit circle. I have to figure out a reference angle. The reference angle is pi over 6. So you can either go to your unit circle for that, or you could inverse tan root 3 over 3. The problem is if you inverse tan root 3 over 3, you're going to get a decimal version. And then you may not be sure that that decimal version is pi over 6. That's why it's better to know your unit circle. Now, let's just get the answers first. I have a positive tan ratio. Tan is positive in quadrant 1 and in quadrant 3. So that gives me pi over 6 and 7 pi over 6 as my answers. Now, if I was to draw that, pi over 6 is right about here, and 7 pi over 6 is right about here. And what I want you to notice is the distance between pi over 6 and 7 pi over 6 is actually pi, which means this is going to form a straight line. So the general solution for tan, I can actually say this in one statement. Remember with the one I gave you a couple examples ago with sine, I had to say it in 2 different statements. I had to say one guy plus 2 pi and the other guy plus 2 pi. Tan works a little bit differently, that often the 2 solutions will be pi away from each other. So I can say it in one statement. I can say pi over 6 plus pi n, where n is a member of the integers. Okay, and then the last question here, we did a couple of things to you. Solve 4 sine x minus 4 cos x equals 0. And it's in the domain negative 360 to 540. So we gave you kind of a wonky domain. And this one's a little different when we solve. So the first thing you probably want to do there is divide by 4. That makes sense. Or just bring the cos over. I chose to bring the cos over before I divided by 4. Doesn't really matter which one you do. So I brought the cos over and I divided by 4. So that leaves me with sine of x equals cos of x. Now, some of you see this as something you can do right away. Some of you may look at this and say, okay, I get this. I'm looking on my unit circle for when sine of x equals cos of x. There's actually 2 spots on my unit circle where the sine of x and the cos of x give me the same thing. That is at pi over 4, where both the sine of x and cos of x are root 2 over 2. And it's at 5 pi over 4, where both sine of x and cos of x are negative root 2 over 2. Some of you, the last 10 seconds you found really, really stressful because you're like, how was I supposed to visualize that? That's okay. You don't have to think about it that way if you don't want to. The next thing you could do, if you didn't see that, is you could say, okay, I'm going to divide both sides by cos. Now, I'm not contradicting myself here. Some of you may say, you just gave me this big warning that I can never divide out a trigonometric function. I'm not dividing out a trigonometric function here, okay? Cos is not going away because it's still here, okay? So we're not making cos disappear. We're just rearranging, and we're gonna do lots of this sort of stuff when we deal with identities. We're just rearranging what it looks like. If I divide both sides by cos, on this side, I'm gonna be left with a 1, but this side gives me sine over cos. Well, you know that sine of x over cos of x is tan of x. So now I can just look at it as tan of x equals 1, and then go back to the same statement. Where does tan of x equal 1? Tan of x equals 1 at pi over 4 and at 5 pi over 4. So 45 degrees and 225 degrees because I'm supposed to be talking in degrees. Sorry, I just realized I got all gung-ho with radians. 45 degrees and 225 degrees. So those are my answers from 0 to 360. Now I think about my window. And my window actually allows me to go from negative 360 to 540. So I start adding 360 to 45. I start subtracting 360 from 45. I start adding 360 to 225. I start subtracting 360 from 225. And I see if all of those are within my domain. I'm going to give you a sec to do that. Figure out what your full answer solution set is. And you should end up with negative 315, negative 135, 45, 225, and 405. The only one that you couldn't do with the ones I just described there was the 225 plus 360. That ended up giving you 585, which was outside of your window. Okay, awesome. So again, just a reminder, do not divide out functions with trigonometric equations. You will lose your solutions. So be very, very careful of that, because if you lose your solutions, you lose a bunch of marks as well. Okay, so your job with this guy is to go through pages 224 to 233. Hopefully this was helpful, and we'll see you soon. Next time we're going to talk about still equation solving, but we're going to get into more quadratic looking equations, which will be like super fun. Okay, take care guys.